Hi and welcome back. So in the last video we talked a little bit about one of our exceptions for electron configurations in the D block, which was chromium. And in this video we're going to talk about our other exception for electron configurations in the D block, which is copper. So I'm going to clear off this drawing again. And let me label my periods again. I've got 1, 2, 3, 4, and that's enough. And so let's figure out what the electron configuration we would expect for copper. What would that be? So if we have copper, and the copper's symbol is Cu. So we'll start out using the Aufbau principle again. So filling up our lowest energy orbitals, we start off with 1s2, 2s2, 2p6, 3s2, 3p6, and now we're at our 4s orbitals. So we start off with, or we go with 4s2, and now we're in our D block. So we're getting ready to put in our 3D electrons. So we count over. We're going to need 1, 2, 3, 4, 5, 6, 7, 8, 9. So what we would expect to put in to our D block would be 3D9, right? And essentially, I guess what I'm going to show you in this video, or I guess I'm really not going to show you, I'm just going to tell you, is that everything for copper is right up to this point, up to 3p6, just like it was for chromium. And really, the exception that we're going to have is going to look very much like the same exact exception that we had for chromium. So everything is going to be the same up to, well, I'll just write it in again. We're going to have 1s2, 2s2, 2p6, 3s2, 3p6. And now at this point, we're going to have, instead of 4s2, we're only going to have one electron in this 4s orbital. So if you remember from the last video, we're going to have a half-filled 4s orbital. And so you can and then what's going to happen to our 3D orbital? Well, we're going to have a totally filled 3D orbital. And again, you can kind of think, maybe, and if you don't understand this, if you didn't understand me talking about in the last video how there is a certain amount of stability associated with a half-filled orbital, or a totally half-filled, if we had one electron in each of our D subshells, don't necessarily worry about that. I'll talk much more about this in the future, but if you did understand it, hopefully you can see here that we've kind of got a similar situation where if we had 4s2, so if we had 4s2 and then 3d9, and we had written out an orbital diagram. So let me actually just go ahead and maybe I'll write something. We haven't really gone into what orbital diagrams are, but if we had, say that's our orbital and we can fit 2 electrons in it, and I'll just represent these 2 electrons by just making 2 notches. We know that our D orbitals that we're going to have 5 of these. So we have 1, 2, 3, 4, 5. And if this was our configuration, remember we're following Hund's rule, that's H-U-N-D. We're following Hund's rule, which pretty much says that we fill 1 electron into each of these orbitals first. So we fill up all the orbitals, and then we start putting in the second orbital, or the second electron into each orbital. So we would put in 1 there, 1 there, 1 there, and 1 there, and now we've got 9 electron in our D orbitals, and we've got 1 unpaired electron. And we'll definitely talk about this more in the future. You don't necessarily have to understand, electron pairings and stuff like that right now, but we've got, in this configuration, we've got 1 unpaired electron, And essentially, the reason that this is the exception, or the reason that that we have an exception here, is because there's more stability if our 4s shell. I'll draw both of these orbitals again. So if we have 1, 2, 3, 4, 5, there's more stability. If we were to just rearrange these electrons, we would have a half-filled 4s shell, which again, there's not a, it's more stable to have a completely filled 4s shell. But, in this situation, there's more stability for the overall atom, for the overall electron configuration, to have only one electron in this 4s shell. Because if we do that, we're able to have a completely filled d orbital shell. We're able to have no unpaired electrons. We're able to completely fill this up. So this situation would be 3d10, and then this would be 4s1 instead of 4s2. Chances are I've probably confused you with writing this stuff down. If I have, don't worry about it at all. It's really not important for what we're going to be covering probably in the next whole bunch of videos. And when we actually start getting into stuff that is important, I'll explain it again, and hopefully it'll make more sense. The important thing to get away from this video, or to take away from this video, is that our two exceptions for electron configurations in our D block are chromium and copper. And chromium's electron configuration I did in the last video, and copper's is essentially this. Copper configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So anyway, hopefully you found this video useful. In the next video, we're going to tackle a little bit of our F block down here. So F block. And essentially, I'm really just going to give you an introduction into the F block. And essentially, I'm going to talk about how you would do total electron configurations for elements past the F block. Doing actual electron configurations for elements in the F block is incredibly difficult because there are loads of exceptions, like we had with chromium and copper. So anyway, I'm actually going to leave you with that. So anyway, I'll start working on the F block in the next video, and hopefully I'll see you there. Thanks for watching.